Ever stop and think about how you're seeing the world right now? That screen you're looking at, a beautiful sunset, or just the plain old blue sky? It's all possible because of the most advanced camera you will ever own. And guess what? You were born with it.
Yep, that's right. Forget the latest smartphone, forget those high-end professional cameras. The most powerful, most amazing camera you'll ever have is your very own eye. I mean, think about it. It's self-repairing, it's got this incredible autofocus, and it's what translates simple light into the vibrant, colorful world we get to experience every single day.
And you know, this comparison to a camera isn't just a fun analogy, it's surprisingly spot on. A camera has a lens to focus light, right? Well, so does your eye. Where a camera has a digital sensor to capture the image, your eye has a light-sensitive screen called the retina. The basic ideas are the same, but the way our bodies do it, well, that's just pure biological genius.
So, how does this incredible personal camera of yours actually work? Let's follow a beam of light on its journey and see how it becomes a picture inside your head.
Okay, first up, light passes through the cornea, which is that transparent outer layer of your eye. The lens then does its job, focusing that light all the way back onto the retina. Now, here's a wild little fact. The image that actually forms on your retina is upside down. It's the retina's job to convert this light into electrical signals that your brain can then flip around and make sense of. Now, this is where the eye really starts to show off and just leaves a normal camera in the dust. It has a built-in, instantaneous autofocus system. It's basically a superpower, and it's called accommodation. Simply put, accommodation is your eye's amazing knack for changing the shape of its own lens. By doing this, it adjusts its focal length, and that's what lets you instantly shift your focus from, say, a mountain far away, to the words right here on this screen. So how does it pull this off? Well, when you look at something far away, these tiny little muscles in your eye, they're called ciliary muscles, they just relax. This allows the lens to flatten out and become thinner, which increases its focal length and brings that distant view into sharp focus.
And for things up close, you guessed it, the exact opposite happens. Those ciliary muscles contract, kind of squeezing the lens and making it thicker and more curved. This shortens the focal length, and just like that, the book in your hands is crystal clear. It's an amazing, constant dance happening inside your eye without you even thinking about it.
There is a limit, though. For most of us, the closest you can comfortably focus on something without any strain is about 25 centimeters. This is what's known as the near point. You can try it yourself. Hold your finger up and slowly bring it closer to your face. You'll feel that point where your eyes really start to work hard. That's your autofocus maxing out. Of course, this super delicate system isn't always perfect. When the eye can't focus light correctly onto the retina, we end up with what are called refractive errors, which is really just a fancy way of saying focusing problems that make our vision blurry. Let's quickly break down the two most common ones. First, there's myopia, or what we all call nearsightedness. This is when light focuses in front of the retina, making distant objects blurry. A concave lens fixes that. Then there's hypermetropia, or farsightedness. This is where light focuses behind the retina, which blurs stuff that's close up. You can fix that with a convex lens.
Okay, so we've covered how the eye captures an image. But what about the colors themselves? Where do they come from? To understand that, we need to look beyond our eyes for a minute and explore the properties of light itself.
The secret to all this color is a phenomenon called dispersion. This is just when white light, like sunlight, gets split into all of its different component colors. You probably remember the acronym from school, right? Roy G. Biv? Red, orange, yellow, green, blue, indigo, and violet. The whole rainbow.
And the most spectacular example of dispersion you'll ever see in nature is, of course, a rainbow. After it rains, the air is just filled with these tiny suspended water droplets, and every single one of those droplets acts like a miniature prism, grabbing sunlight and splitting it into that beautiful arc of color.
And here's exactly how that works. First, sunlight enters a water droplet and it bends, or refracts, and that starts the color separation. Second, that light bounces off the inner back surface of the droplet. And third, as the light leaves the droplet, it refracts again, spreading the colors out even more for our eyes to see.
Now, this same principle of light interacting with tiny particles in the atmosphere, it also answers another one of nature's biggest questions. I'm pretty sure we've all wondered about this at some point.
So why is the sky blue? It's not because the air itself is blue, and nope, it's not a reflection of the ocean. The real answer has everything to do with something called light scattering.
So here's the key. Earth's atmosphere is filled with all these tiny molecules and fine particles, and it turns out These little particles are way better at scattering light with short wavelengths, like blue and violet, than they are at scattering long wavelength light, like red and orange. So as sunlight streams in, that blue light gets scattered all over the place, filling the sky and eventually reaching our eyes.
This also totally explains why the sky looks black to an astronaut in space. With no atmosphere, there's nothing to scatter the sunlight, so the sun is just this brilliant point of light against a dark background. Our blue sky is really just a beautiful side effect of our planet's atmosphere doing its thing.
So from the incredible mechanics of our eyes to the physics of light in our atmosphere, how we see color is a pretty amazing story. But it leaves you with a final thought. The whole rainbow of colors we can perceive is just the visible spectrum. It's a tiny, tiny fraction of all the light that actually exists. It makes you wonder, doesn't it? What else is out there, just beyond what our amazing biological cameras are able to see?